Hi, my name is Kendrick, and the title of my project is Count Me Once, Count Me Fast. Suppose we're collecting real-time viewing data for a particular ad, and we want to know the total number of unique viewers in a specified time period. Structures like bitmaps can be used to get exact counts, but they require memory in proportion to the number of unique items to be counted. In contrast, an algorithm known as hyperloglog uses a structure that is fixed in size and relatively small. Hyperloglog structures can be used to track billions, if not trillions, of unique items super efficiently. But as the saying goes, there is no free lunch, and the trade-off is the count we get is not exact. Fortunately, for many real-world applications where we might need to count hundreds of millions of things, an approximation is usually sufficient. How does hyperloglog work? Suppose we generate a binary number at random. It is unlikely the number begins with a long string of zeros. For example, the chance the number will have, say, 6 leading zeros is low, less than 1%. Now this is rare, but not that rare. In fact, if we generate 128 numbers at random, we'd expect one of them to have 6 leading zeros, and the others to have 5 or fewer, on average. Now, suppose we're given a list of n numbers, but we don't know n. However, we observe that one number in the list has 6 leading zeros, and the others have fewer. Based on these probabilities, we can estimate the number of unique items to be around 128. Why is that? Well, if my list were much shorter, we would not likely see a number with as many as 6 leading zeros. And if my list were much longer, we would likely see a number with many more leading zeros. Hyperloglog processes binary representations of the IDs we are counting in this way. For each of multiple buckets, it stores only the maximum length of leading zeros of all numbers in that bucket. An average is then computed and converted into an approximate count. I constructed a pipeline to process simulated ad view data using Twitter's algebraic implementation of hyperloglog. I used Kafka for ingestion and Spark streaming for processing on a 4-node AWS cluster. In one exemplary run, I pushed 1 billion records through the pipeline, which took about 3 hours to process. More specifically, for longer streams, I was able to process roughly 100,000 records per second. And for streams with fewer than 1 million records, these were processed in less than a minute. I also measured the error in the total count of unique IDs, which generally ranged from 1 to 3%. Interestingly, when I calculated counts for two subgroups and combined their hyperloglog structures to get a count for the intersection, the error rate typically increased. It turns out improving count accuracy for intersections using hyperloglog is an ongoing area of research. Finally, I compared hyperloglog to an implementation where I maintained a central set of actual IDs observed. Set structures can give exact counts, but take up a lot of memory and require more time to process. When using sets, I found that Spark reaches a point where it can't keep up with incoming data, causing system instability. As an extension of my project, I addressed an issue relating to computing counts for subgroups. I previously assumed segment information was encoded within the stream or extracted from the user ID, but it may be more realistic to assume we would need to retrieve it from a database. This is not a problem if we were to do batch processing on historical data, but repeatedly fetching from a remote database when performing real-time processing is problematic. In my solution, I used another probabilistic data structure called a Bloom filter to quickly determine whether a user belongs to a specific segment. This structure can be pre-computed and stored on each node, avoiding the need for database accesses.